Okay, we're going to wrap up our first trig unit today by doing lessons 8 and 9. So just as a really quick review, what we've learned about sine functions is that the sine function, the regular straightforward sine function, starts at 0 at the origin. It goes up to a maximum of +1 and down to a minimum of -1. And it has a period of 2 pi. Okay, so this would be your sine function. Your regular straightforward cos function is very similar, except that instead of starting at the origin, it would start at your maximum of 1. It has a minimum of -1, and it still has a period of 2 pi, but it starts high, goes down to the minimum, and then comes back to the maximum again. Okay? It also has a period of 2 pi, just like the sine function does. In fact, the only difference between them is that if you took the sine function and shifted it 90 degrees over, you'd get the cos function. Or if you took the cos function and shifted it 90 degrees the other way, you'd get the sine function. So let's just make a note about that. A horizontal translation by pi over 2, which is 90 degrees, will turn a sine curve into a cos curve. Okay? So what lesson 9 and lesson 10 are both going to do is just see if we can take what we've learned about sinusoidal functions. So that's just a really long, crazy looking word that just means the sine or the cosine functions. Okay? So the name is a little misleading because it's not just the sine functions, it's sine or cos. And once we graph them, if we can read the information off of the graph, and if we can tell what the graph is giving us, what information it is giving us, and also if we can take information that we're given and convert it into the equation and come up with the equation of the graph. Okay? Now, when occasions when you would actually use graphs of sinusoidal functions are any time in our day-to-day life when certain phenomena are happening periodically, a regular repeating pattern, a cyclic pattern. Okay, so this includes things like the examples given here, the time of sunrise as a function of the day of the year. So as we know, there's the shortest day of the year in December, 21st, I believe it is, and the longest day of the year, which is June 21st. And the sun rises at a different time each day of the year, getting later and later and later as you get closer to the shortest time of the year, and earlier and earlier and earlier as you get closer to the longest day of the year. Okay, so at any given time there are 2 days in the year where the sunrise is at the same time of day. Okay, and so year after year after year, that's repeating on a repeating periodic interval. Also, whenever you're measuring the cycle of a wheel or a tire or a Ferris wheel, this is also as a function of time because that is repeating over and over and over as the wheel turns, the rotations of the wheel. Also, another one is the depth of ocean waves because of the changing tides. Tides coming in and tides going out at regular intervals. This also could be modeled using a sine function or a cosine function. Okay, so this paragraph down here just says most of the equations used will be functions of time, and so the variable that you'll use instead of x often is t for time. Okay, although once in a while instead of y you'll see that it is t as well. Okay, the period of the graph, then if your x-axis was t in time, then the period of the graph, the distance that graph travels to do one complete cycle, would be in time units then, right? In hours or in minutes or in seconds. Okay, then we're going to use our graphing calculators to figure out suitable graphing windows, because that's a really important skill to be able to do, as well as to calculate certain points on the graph. Okay, so let's have a look at class example number 1. It says the depth, d meters, of water in a harbor t hours after midnight can be approximated by the function the depth as a function of time is equal to 12 plus 5 cos 0.5 t, where t is between 0 and 24. This gives you your domain right there, okay? Now, let's just have a look at what this equation is really saying. This d as a function of t, this is like, we've looked at functions like g of x, f of x. This is just d of t, okay? So the depth of the water as a function of time, so over certain intervals of time, is, okay, so the d of t, really, that's your y, okay? And in this case, your x would be t, right? Because it's time. Okay, so the problem with this equation is that it's not written in standard form. It's not written in a form where we can actually read our parameters a, b, c, or d off of it, because it's not in the form that we're used to seeing it in. So if that happens, all you have to do is rewrite it, rearrange it so that it is, okay? So the depth of the waves in terms of time is equal to 5 cos 0.5 t, and then we'll put the plus 12 at the end, because that's our that is our midline, that's our d, right? Okay, now we can actually identify that our a is 5, our b is 0.5. In this case, there is no c, so I'm going to just write that c is 0, and our d would be 12. Okay, so we've identified now each of the parameters so that we'll be able to graph this function. Okay. Now, A asks us to determine the maximum and the minimum depths of water in the harbor. Okay, well, we have a formula for figuring out the maximum, and the maximum is d plus a. That's our midline plus the amplitude, the distance from the midline to the highest point. And so our d is 12, our a is 5, so 12 plus 5 equals 17. And if this is our maximum point, okay, this is on our y-axis, and so this is depth in meters, right, that we're going to be graphing. Okay, minimum point is d minus a. So this is 12 minus 5, which is 7, and again in meters. Okay, so let's just draw ourselves kind of a sketch on this side of the page where you have a little room, what this would look like if we were graphing this. Okay, we know that we have a maximum point here at 17. We have a minimum point down here at 7. Okay, now we have to figure out what our midline would be. We probably can figure it out from that, but we also have an equation, and the equation for the midline is 17 plus 7 divided by 2. So 17 plus 7 is 24 divided by 2, that's 12. So our midline is 12. So right across here, right in the middle between our highest point and our lowest point would be our midline of 12. Okay? All right, now we need to figure out the period, and once we have that, then we can sketch our function. Okay? So period is 2 pi over b. Okay, do we know what our b is? Yes, we do, right from this equation here. b is 0.5. So 2 pi divided in half, in other words, is 4 pi. Okay, and if this is the period, this is the distance that it takes for one whole cycle on this graph. Okay, one whole repeating period of this graph is 4 pi. Okay, so this is in hours, isn't it? Okay, it told us that our x was t, really, so this is time in hours, and our y-axis is really the depth in meters. Okay, so our period is 4 pi in hours. Okay. Okay, so what we have happening here then is our graph, if we have to figure out where we're going to start our graph, we know that this is a coast graph. Okay, so a coast graph normally starts high unless it has been reflected over the midline. In this case, it hasn't because we've got a positive 5. So it is actually starting at an amplitude of 5 above the midline. So it's actually starting at the maximum point. It's going down to the minimum of 7, back up, and it's just continuing like this. Okay? All right, let's see if we can figure out a suitable window that could be used to display this graph. Okay? So we need to figure out then what would be suitable parameters for our x. Well, if our x is time, it tells us right here, okay, that our domain is from 0 to 24. So 0 hours to 24 hours, okay? So in other words, they've given us our parameters for our x-axis. So we're going from 0 to 24, and you can go up by any scale, sometimes 1, sometimes 2. Since we have a span of 24 units, let's go up by 2. Our answers could vary on this. We wouldn't all necessarily have to have the same thing, as long as you can see your whole graph, one whole period at least of your graph. Now your y values, you want to be able to see your maximum points so that you could calculate them if you wanted to on your calculator, and your minimum points. So usually it's wise to go a little bit below your minimum, a little bit above your maximum. So in this case, let's go from 0 up to 20. And again, you could go up by 1s, 2s, 5s, wouldn't really matter. Okay, as long as you can see that maximum point and that minimum point if you needed to calculate those on your calculator. Okay, now D is an interesting question. It says, what's the depth of water to the nearest tenth of a meter at 2 o'clock in the morning? Okay. Well, first of all, this is really important, and really watch for this on the test. When they ask you to give a value to the nearest tenth or to the nearest whole meter, be really aware of that and really watch that, because you could calculate the answer correctly, but if you list it in a different format than to the nearest tenth of a meter, you would get that answer wrong, even if you've done all the work right. So please be very careful of that. Watch for that, okay? So this is saying, what's the depth of the water at 2 o'clock in the morning? Okay, well, think about this for a minute. What does this 0 represent? And this 24? Okay, go back to your original question. The original question was saying, in hours after midnight, okay? So 2 o'clock in the morning would be 2 hours after midnight. So in other words, like right about here. Okay, so what it's asking you is, what's the depth of water at when your x value, your time, is 2? Okay, so in other words, what's this point here on the graph when your x is 2? What's your y? How do you calculate that? You'd use your calculator, wouldn't you? So on your calculator, you're going to go second button, and you're going to ask it to calculate a value when x is 2. Okay, and if you plug that in, it's going to tell you that your y, in terms of this graph, that's your depth in meters, is 14.7 when your x is 2. All right, I love this next question because it says, a ship which requires a minimum of 8.5 meters of water is in the harbor at midnight. By what time to the nearest minute must it leave in order to prevent it from grounding? Okay, so what this graph is showing is that we have a depth of water that is changing periodically over regular intervals. That's the tide coming in and the water level rising, and the tide going out and the water level declining, okay? So what's happening here is this boat, this ship, is fine from midnight, where 0 is, from midnight to here while the water is above 8.5 meters, okay? But once the water gets here at 8.5 meters deep, okay, once the water gets there, then that ship would run aground, okay? So here, this point here would be a problem. It would be stuck, okay? But at this point, where the water level is above 8, you're fine, okay? You would run aground here, where the depth of the water is less than 8, but then once the tide comes back in and the water level is again above 8, your ship is okay in this whole section here. But then again, when the tide goes out and your water level is below 8.5 meters, your ship would again get grounded, okay? So this question is asking, what is the point to the nearest minute that this ship has to leave in order for it not to hit this point, just below 8.5 meters, or that ship is grounded? So we need to know this point right here, okay? Now, how am I going to get, if, like, I don't know my x, that's what I'm trying to get, okay? I know my y has to be 8.5 meters. I need a horizontal line drawn right across my graph right there. That's a linear equation right across at a value of 8.5. How do I get that? Well, I'm going to graph two equations then. I'm going to graph as my y1 the original equation, which was, and I can put it in either format, the one they give me right here, or I can put it in the rearranged format, either one, because they're the same thing. And then for my y2, I'm going to say my y has to equal 8.5. And that will give me a linear equation, a straight line horizontally across at the value where y is equal to 8.5 meters. Okay? So once I get that, if you want to just pause the video for a minute, put those two graphs into your y1 and y2, and then restart the graph once you have that. Okay, and you should get something like this. Okay, so I am trying to calculate now this point right here, this point of intersection. So if you remember, you go into second, you calculate, number 5 is intersect, and this is the one where you just ride your cursor around to that point of intersection. You don't go past it, you go as close as you can on it, and then you hit enter 3 times, and when you do that, it tells you when your y is 8.5, your x will be 4.6923,876. Okay, let's write that whole value down. So it intersects at x equals 4.6923,876. Okay, now let's think about that for a minute. What does that really mean? If my x value is 4.69 blah, 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 what does that really mean? It means at 4 hours after midnight and a decimal of another hour, like 0.6923876 of another whole hour, okay? So how do I figure out how much that is, how many minutes that is? I have to multiply that by 60. 0.6923876 times 60, and that's going to give me 41.54 minutes. Okay, so it's at 4 hours after midnight and 41.54 minutes. Okay, but this question asked me to list this to the nearest minute. What time does that ship have to leave the harbor before it will get grounded? Okay. So let's think about that in terms of this question, because normally I would round this then to 42 minutes, right? But think about that for a minute. If this point right here is 4 hours and 41.54 minutes, then if I round it to 42 minutes, we're down here, right? 42 minutes just keeps going just a little bit further, and by that point, that ship is grounded. It's too late. So in this case, instead of going with regular mathematical rounding rules, I have to look at the scenario and I have to say to myself, would it make sense to round that up to 42? At 42 minutes, that ship is grounded, so no, it wouldn't. So in this case, I'm actually going to round down and to 41. Okay, so if that's the case, then that ship needs to leave the harbor at 4 hours after midnight, which is 4 o'clock, and 41 minutes, 4:41 a.m. That ship needs to be out of the harbor, or it will get grounded. Then the question says, what's the next time to the nearest necessary minute that the ship can return to the harbor? Okay, well, looking at our sketch again, okay, remember the ship is grounded here, the water level is less than 8.5 meters, and so the ship can't be in the harbor here. But the ship could safely return here, because then the water level will be greater than 8.5 meters, right? Okay, so at this point, we need to figure out that or calculate that point of intersection. So again, you go back in, ask your calculator to calculate the intersection point, ride your cursor around to that point, land it right on that point, and hit enter 3 times, and it tells you that when y is at 8.5, your x is 7.9148936. So it intersects at 7.9148936. And again, this is 7 hours after midnight and a decimal of an hour more, so I have to multiply that by 60. And when I do that, I get 52.43 minutes. Okay, now I have to think, am I going to round that down like I normally would? Okay, or am I going to round it up? What makes sense in this situation? Okay, well, at 7 hours and 52.43 minutes, we're right here. Okay, so if I round it down, we're right here. Okay, that ship will be grounded there. So I need to round, in this case, I need to round that up to 53. So at 7:53 a.m., it would be safe for that ship to return to harbor. Okay, let's flip over the page and we'll have a look at the second example. This is another scenario where you may see the sine function modeling this situation. This is a certain town in Alberta where they have calculated the time of sunrise for any day of the year using this particular formula, where in this case T is the time in hours after midnight again, and D is the number of the day in the year. So whether it's the 50th day or the 200th day, okay? So in this case, our T is actually our Y, and our D, the day of the year, is actually our X, okay? So in this case, T is in hours, that's your Y-axis, and your X is day of the year, okay? And we need to figure out a suitable window that we can use for displaying this graph. Okay, well, if our D is the days of the year, then we're going to be going from 0 days to 365 days of the year, right? That makes sense, okay? But we don't know what our Y's, what our times will be, because we don't know our maximum and minimum values yet. So let's figure them out. Our maximum value is going to be D plus A. Okay, our D is 6.3, and our A is 1.79 or negative 1.79. How do you know whether you're going to include that negative sign? Okay, well, if this is our A, this is our amplitude. Okay, amplitude is the distance from the midline to your highest point or the midline to your lowest point. Is it possible to measure distance in negatives? No. Okay, so you're going to take the absolute value of that. This negative sign in front, that just tells you that this graph has actually been reflected over the midline. Okay, so don't worry about that negative sign. Just use the absolute value, the amplitude, which would be 1.79. So that's going to give you 8.09. And we need to figure out what our unit would be. Okay, if this is the maximum point and we're measuring vertical distance or on the vertical axis, time in hours, this is 8.09 hours then. Okay, your minimum point would be D minus A, which is 6.3 minus 1.79, and that's going to give you, 4.51. And that's again in hours. Okay, so what would be suitable window? Well, our x's would be then from 0 to 360. And again, that's a really large span, so probably wouldn't go up by 1s or 2s or even 5s. In fact, you may even go up by months, so 30 days. And then your y's, again, you always want to see a little bit higher than your maximum point and a little bit lower than your minimum point. So I would go from, like, say 2 up to 10, and you could go up by 1s or 2s, or it doesn't really matter. Okay, as long as you'd be able to see your maximum point and your minimum point to calculate them if you needed to with your calculator. Okay, now we do have a little bit of a horizontal shift here. It would be some number minus 78 divided by 365, so it's a very, very tiny little shift. So what you would have happening here is you have a maximum point of 8.09. You have a minimum point of 4.5. Okay, and so what you have happening would be something like this. Okay, and then it would be going over like that. Okay, so the next question, B, says use this formula now to determine to the nearest minute when the sun rose on May 7th, which was the 127th day of the year. Okay, well, if these are the days, the 127th day of the year would be like somewhere here, right? So we want to find the time that the sun rose. So we want a time on the vertical axis. We want to know what's our y when our x is 127. Okay, how do I calculate that? Well, again, you're going to go second. You're going to ask your calculator to calculate a value when your x is 127. And it's going to tell you then that your y, or in this case, your time, would be 4.96292 hours. But again, this is 4 hours after midnight and a little bit more. So we need to multiply that by 60 to see how many minutes is that. And that is 58 minutes to the nearest minute, because it asked us to add it to the nearest minute. Okay, so in other words, this is 4:58 a.m. because it's 4 hours and 58 minutes after midnight. All right, and now C is asking determine on which days of the year, days plural, the sun rose at 7 o'clock in the morning. Okay, well, on our scale here, 7 o'clock in the morning would be right about here, and we want to know, like, what's this? Okay, what days of the year did that happen? So this point and this point, and then this is actually starting the whole cycle all over again. Okay, so we just want these 2 points. Okay, so we need to calculate, we need a horizontal line, a linear function again, going across at 7 o'clock in the morning so that we can find the intersection point of those 2 points and know what our x is then, what our times were. Okay, so again, you're going to graph y1 will be the original function that they give us. I'm not going to write that all out, but if you could plug that into your calculator in your y1, then you would graph in your y2 equal to 7 to get this horizontal linear function, and then you would calculate the intersections, and they would intersect at x equals 54.659, and it goes on and on and on, and x equals 283.840, and it goes on and on and on. But because this asked us for which days of the year, you wouldn't really have part days or decimal days. So you would say on days, and you would use regular rounding rules. It makes sense in this case. Day 55 and day 284. Okay. All right, we are going to edit this assignment a little bit. I would like you to do questions 1, 3, 6, and 7 so that you get experience with these questions and modeling actual situations that have a repeating period to them with sine and cosine functions. But we are going to do the second half of this lesson first, and then you'll have time to go back and do these questions as well as the couple questions that we're going to do with the next lesson as well. But I am going to record the next lesson in a separate file just so that the computer doesn't glitch on us. So please watch the second video before you come back and do the assignments, okay?